Let's take a look at an example, and one that would, I think, illustrate rather well a time it may be nice to use Green's theorem. So I want to evaluate the line integral that's given by um, x y dx plus x squared dy. And obviously this is indicating that we're integrating over a closed curve where c is defined by these vertices. So let's draw a picture of this first to see what we're dealing with. See, I'm at 0, 0. And then out here to 3, 0. And then I'm at 3, 1. And then back to 0, 1. So it looks like I'm dealing with this rectangular region. And of course I have positive orientation, so I know I'm heading in this direction like this. Okay, I need to label this, so I'm going to call this C1, this C2, this C3, and this C4. So what I can do is I'm just going to evaluate this line integral the way I normally would, breaking it up into 4 sections and take it piece by piece, and I'm going to parameterize each section as a function of t. So looking here at C1, I'm going to let x be equal to t, and of course y is 0. That would then tell me that dx equals dt, and of course dy equals 0 dt. And specifically, 0 is going to be less than or equal to t, which is less than or equal to 3. So I need to go from 0 to 3 here. For C2, I'm going to be traversing this piece right here. X is a constant 3. And that tells me, I guess, let's do dx right away. So dx equals 0 dt. In this case, I'm going to let y be equal to t. That means that dy is going to be dt. And of course, t in this case is going to end up going from 0 to 1. Now this next segment, C3, I'm going to look at this and say, well, gosh, x is going to be equal to 3 minus t if I let t go from 0 to 3. That would also give me dx in this case is equal to a negative dt. Y is going to be equal to 1, so dy will be equal to 0. And so you have 0 less than or equal to t, which is less than or equal to 3. So t is going to go from 0 to 3. This last part, C4, when I traverse this piece, see, x is going to be equal to 0. Obviously, then dx will be 0 dt. And y is going to be equal to 1 minus t if I let t go from 0 to 1. Whoops, there we go, from 0 to 1. So dy is going to equal negative dt. Now I have all the pieces that I need. So let's see, get a little bit more room here. So this line integral over c1 plus c2 plus c3 plus c4, that's my curve. I'm going to take this piece by piece by piece, of x, y, dx plus x squared dy. See, I need the dx and dy for each segment here, so I can substitute that in. And again, I'm going to break this down piece by piece so we can evaluate it. Scoot this down a little bit. We need to keep an eye on this. So my first piece, and this is actually, let's just say for C1. For my first piece in reference to C1, I'm going to have the integral from 0 to 3 of xy. Well, x was t, y was 0, dx, which dx was just dt, doesn't matter because that 0's there anyway, plus x squared, well, x was t, so this would be t squared, dy, and dy was 0 dt. So this whole thing is going to be 0. So I didn't have to worry about that. Now C2, that piece that went up, I'm going to integrate this from 0 to 1. And I need x times y. Well, x was 3 there everywhere, and y was equal to t. So it's just 3t. Times dx. Well, dx was 0 dt, so that piece goes away. Plus x squared. Well, x was 3, so 3 squared is 9. Dy, and dy was just dt. Okay, cool. I finally have a piece here. So when I integrate this, this is going to be 9t from 0 to 1. So this is going to contribute a total of 9. So I'm going to have this integral. This is the x was 3 minus t, and y was 1, and I had a negative dt, and t went from 0 to 3, plus x squared, which was 3 minus t squared, dy, and in this case dy was 0 dt, so that's going to go away, but I can integrate this. So let me see, I'm going to integrate this, and I'm going to end up with a negative of, because this negative right here, this will give me 3t minus t squared over 2 evaluated from 0 to 3, which is going to be a negative 9 minus 9 over 2, which is negative 9 halves. So that's the contribution from C3. And then this last curve, C4, see, that's going to be, see, x was 0, y was 1 minus t, and dx was 0 dt, so that contributes nothing. And also t went from 0 to 1 here. See, plus x squared, which was, well, 0 squared, dy, which is negative dt, not that's going to matter. That's going to contribute nothing. So what I'm going to have is this original line integral of xy dx plus x squared dy is going to be equal to 0 plus 9 minus 9 halves plus 0, which is just 9 halves. Now that was quite a bit of work, but look what happens if I go ahead and use Green's theorem. So based on Green's theorem, I'm going to say that this integral over this simple closed curve, C, and this is piecewise smooth, of xy dx plus x squared dy, I can look at as being the double integral over d of the partial of q with respect to x minus the partial of p with respect to y. And that's going to give me the double integral over this region D of the partial with respect to x of q, which is x squared, minus the partial with respect to y of p, which was xy, dA. that's going to be the double integral over the region of 2x minus x over that region. And recall this region looks like this. So I'm thinking that this is going to be the double integral of 2x minus x. Why? Let's see here. Which way do I want to go on this? Let's do dy dx. Yeah. dy dx. Y is from 0 to 1. And x is from 0 to 3. So let me scoot down a little bit more. So this is going to be, like I normally do, kind of break up this one piece I'm going to be working with. Clearly, this is just going to be 2x minus x, because there are no y's here. So I'm going to put a y in each of them, evaluate from 0 to 1, so it's just 2x minus x. So this is the same as the integral from 0 to 3 of 2x minus x dx, which is going to be x squared minus x squared over 2 evaluated from 0 to 3, which is 9 minus 9 halves, which is 9 halves, exactly like I was supposed to get. Now look at this, and then look at this. There we go. Yep, there's the end, or the beginning, however you want to look at it. And you can see there are definitely some scenarios where Green's theorem would really come in handy.